Have you ever really looked at a simple idea on paper and then looked at the complex reality it creates and just thought, how? Today, we're diving deep into that very journey, pulling back the curtain on how we get from a single molecule to a sprawling, world-powering megaplant.
So check this out. On the left, you've got this elegant, simple chemical reaction. This is how you make a chemical called aniline. Looks neat, right? But then you look at the right. That is what it actually takes to make the reaction happen in the real world. That's the blueprint for the entire factory. The difference between the two is it's staggering.
So, that's the big question we're going to tackle. How do engineers bridge that enormous gap? How do they take that clean, simple idea and turn it into a complex, functioning, and most importantly, safe piece of industrial reality? Well, it's a story of science, smarts, and some really clever problem solving.
Okay, so before you even think about ordering steel or drawing up plans, you have to ask the most fundamental question of all. You have to go to the ultimate authority, the laws of physics. And the question is, does nature even allow this reaction to happen?
To get that answer, we look at something called Gibbs free energy, or delta G. You can think of it as the universe's bouncer. It stands at the door of every possible chemical reaction and decides who gets in. It's the ultimate go or no-go signal.
The easiest way to think about delta G is like a traffic light. If it's a negative number, that's a green light. The reaction is spontaneous, which means it wants to happen. If delta G is positive, that's a hard red light. Nature says, nope, not happening. And if it's exactly zero, that's your yellow light. It's a state of perfect balance, called equilibrium. A perfect example is water boiling. It happens at exactly 373.15 Kelvin, because at that one temperature, its Gibbs free energy is zero. It's perfectly balanced between liquid and gas.
But, and this is a huge but, here's where the engineering magic kicks in. Even if nature gives you a red light under normal conditions, you can kind of change the conditions. By cranking up the temperature or the pressure, engineers can actually nudge that delta G value and turn a no-go into a go. This is the secret sauce behind countless industrial processes.
So, once we've gotten the green light from the universe, it's time to start planning. We need a map, right? A master plan that lays out the entire factory so everyone knows what to do. And that master plan is called a process flow diagram, or PFD. Honestly, this is probably the single most important document in the whole design process. It's the universal language for chemical engineers, showing every pump, every vessel, every pipe, and how the whole thing fits together.
So when you start sketching out a PFD, you almost always start in one place, the reactor. This is the heart of the plant. It's the box where the magic happens, where your starting chemicals get transformed into the product you actually want.
But here's the catch. The real world is messy. As this textbook quote says, reactions are almost never perfect. You don't just get your product, you get other junk, byproducts, and a lot of your starting material doesn't even react. So, what do you do with all that leftover stuff?
This is where the blueprint starts to get a lot more complex and a lot smarter. Engineers add more equipment. See this tall tower here, T100? That's a distillation column, designed to separate the pure product from all the other gunk. And that loop, RCI1, that's a recycle loop. It takes all the unreacted material and sends it right back to the beginning to try again. It's brilliant. Nothing is wasted, and it makes the whole process way more efficient and profitable.
Nowadays, this entire complicated dance is planned out on a computer. Using incredibly powerful simulation software, engineers build a complete digital twin of the plant. They can tweak it, test it, and optimize it for months, sometimes years, making sure everything works perfectly in the virtual world before a single piece of actual steel is ordered.
All right, so the virtual blueprint is flawless. Now for the really exciting part, making it real. It's time to turn all those lines and symbols on a screen into tons and tons of actual steel, concrete, and pipe.
And every single symbol on that PFD, it just explodes into this incredibly complex piece of real-world hardware. That simple little circle for a heat exchanger, it becomes one of these highly specialized designs, each one carefully engineered for a specific job, all standardized so everyone's on the same page.
And the scale we're talking about is just immense. This isn't just chemistry anymore, it's hardcore mechanical and civil engineering.
I mean, look at this diagram. It shows a support skirt for a giant vessel. This thing has to be strong enough to hold up hundreds of tons of steel and chemicals against immense pressure, wind, and sometimes even earthquakes. Of course, choosing what to build it all out of is a massive decision on its own. Basic carbon steel is your baseline. But if you're dealing with nasty, corrosive chemicals or crazy high temperatures, you need the heavy-duty stuff, like Monel or Inconel. They perform way better, but man, do they cost more. It's this constant balancing act between cost and performance.
Okay, so you can build the plant, but will it run safely, and will it make any money? This brings us to the final, and you could argue the most critical layers of the design, safety and economics.
To make sure a plant is safe, engineers do something called a HAZOP study. It's basically a highly structured way of playing the what-if game. They break the whole plant design down, piece by piece, and ask, what if the flow stops here? What if the pressure gets too high there? They imagine everything that could possibly go wrong and then design safeguards to make sure it doesn't.
And the economic stakes? They are absolutely gigantic. This number, it's just from one example in a textbook, but it shows the estimated cost to build a plant like this. Over $433 million. When you're spending that kind of money, you have to be 100% sure you got the design right. And getting it right isn't just about the upfront price tag. It's about trade-offs. This chart shows a classic engineering dilemma. You could spend less money upfront on cheaper equipment, but then your energy bills to run the thing will be huge for decades. Or you could invest a lot more in super efficient gear and save millions in energy costs over the life of the plant. That's what optimization is all about.
But at the end of the day, the best philosophy for designing a safe plant comes down to this absolutely brilliant quote from a safety pioneer named Trevor Kletz. Material that is not there cannot leak out. It's so simple, right? The safest, best design is one that, by its very nature, uses the least amount of dangerous stuff in the first place.
So there you have it. From the fundamental laws of thermodynamics, to a complex digital blueprint, all the way to a multi-million-dollar machine built on a knife's edge of trade-offs between cost, safety, and efficiency. It's an incredible process. And it really makes you look around and wonder, what other incredible, unseen designs are powering the world you and I live in every single day?